Section 3.4, the chain rule. If g is differentiable at x and f is differentiable at g of x, then the composite function f equals f composed with g, defined by f of x equals f of g of x, is differentiable at x, and f prime is given by the product f prime of x equals f prime of g of x times g prime of x. So what this means is that if we have a function of another function, then we can find its derivative by first just taking the derivative as if there wasn't another function inside, and then multiplying by the derivative of whatever was inside. This is not the easiest theorem to prove, so we omit the proof. You could check it out in some different books. They have different proofs. However, it might make a little bit more sense if you consider this in Leibniz notation. If you let y equal f of u and u equal g of x, then you have dy dx equal to dy du times du dx, where the rate of change of y with respect to x, if y depends on u and u depends on x, is equal to the rate of change of y with respect to u times the rate of change of u with respect to x. So that should kind of make sense. You can even visualize the du's is canceling with each other and leaving you with dy dx. However, you have to be a little bit careful with that, because even though we write these to look like fractions, they are not actually fractions, even though they have a lot of the same properties. So let's do an example and find f prime of x if f of x is the square root of x squared plus 1. So in this case, f of u is equal to the square root of u. So that means that f prime of u is equal to half of u to the minus 1/2, which is the same as 1 over 2 rad u. So notice in this case, we are just looking at the derivative of the square root function. We're not caring about what's inside the square root function. We're just pretending that this entire thing is basically just an x. So we're just taking the derivative of square root of x. But since we already have an x, we're calling it u. Okay, so now let's take the entire derivative. So big F prime is equal to f prime of g of x times g prime of x by the chain rule. F prime of g of x is f prime of u, and then we'll just swap out u for g of x. So it was supposed to be 1 over 2 times square root of u. However, we said that u would be g of x. So instead of putting u inside, I'm going to put in g of x's, which is x squared plus 1. And then multiply by the derivative of u. So I multiply by the derivative of g prime. So I multiply by the derivative of what I put inside. So it's the derivative of x squared plus 1, which is just 2x. So then this simplifies to x over the square root of x squared plus 1 when we cancel out the 2's. So you can see that every single time we do this, we're going to pretend that one function is just of a single variable, basically. We take the derivative of the outer function with respect to that single variable, then we swap back in what was really inside without taking the derivative, and then after we swap it in, we multiply by the derivative of what we put in. Let's differentiate y equals sine x squared and y equals sine squared x. So for a, dy dx is equal to the derivative of sine x squared. So we're going to pretend that the inside is just x. So if it was sine of x, derivative would be cosine of x. So that means this is cosine of x squared. However, the inside wasn't x. There was a function inside. So we have to take that derivative, and we get 2x. Okay, so then we can just put the 2x out in front. Why not? So it's 2x cosine x squared. For b, we're looking for dy dx. So that is the derivative of sine squared. But sine squared is a shorthand notation for sine of x squared. So this is the same thing as sine of x squared. So we're going to pretend that this is just an x squared function. Derivative of x squared is 2x. So derivative of sine x squared is 2 sine x. But then we have to multiply by that thing inside. I mean the derivative of that thing inside. Derivative of sine is cosine. So we multiply by cosine. You might remember that 2 sine x cosine x is actually a trigonometric identity for the double angle formula. So you don't have to do this, but you could rewrite this as sine of 2x. So this brings us to our next theorem, the power rule combined with the chain rule. If we have n as any real number and u equals g of x is differentiable, then the derivative of a power function u to the n will be n times u to the n minus 1, just like our power rule was, except that we also have to multiply by the derivative of u. So this would be the same thing as if u is g of x, we have derivative of g of x to the n, be n times g of x to the n minus 1 times g prime of x. So if u equals g of x is equal to x cubed minus 1, then n would be 100 in this case, because we have x cubed minus 1 to the 100th power. So by our theorem, dy dx would equal the derivative of x cubed minus 1 to the 100. The 100 would hop out in front, just like with the power rule. We're pretending that the x cubed minus 1 is basically just a single variable. So that stays, and then it goes to the 99th power. However, we have to also multiply by the derivative of what was inside. So we multiply by the derivative of the x cubed minus 1. That ends up becoming 100 times x cubed minus 1 to the 99 times 3x squared, which is just 300 x squared times x cubed minus 1 to the 99. Let's find f prime if f of x is this 1 over cube root mess. Well, it's a cube root, we could write that to the 1/3 power, and instead of leaving it in the denominator, we could put it in the numerator if we made the exponent negative. So let's rewrite this to the negative 1/3. So that means that f prime of x is equal to minus 1/3 times x squared plus x plus 1 to the minus 4/3 times the derivative of what was inside. This x squared plus x plus 1 business. Okay, so that's minus 1/3 times x squared plus x plus 1 to the minus 4/3 times 2x plus 1. So all we did was pretend that this inside here was just an x to the minus 1/3. The minus 1/3 would hop out in front, and then the exponent would be reduced by 1. Minus 1/3 minus 1 is minus 4/3. Let's find the derivative of the function g of t minus 2 over 2t plus 1 to the 9th power. So unfortunately here it looks like we have to use a quotient rule at some point, because we have a quotient. So let's first use the chain rule. The 9 hops out in front, because we're going to treat this entire thing like it's one variable. It's like x to the 9th. So it becomes 9 times t minus 2 over 2t plus 1 to the 8th. And then we multiply by the derivative of what was inside. So that's t minus 2 over 2t plus 1. And we have to take the derivative of that. So that's 9 times t minus 2 over 2t plus 1 to the 8th. By the quotient rule, we take 2t plus 1 times derivative of t minus 2. Derivative of t is 1, derivative of minus 2 is 0, so it's times 1, minus derivative of 2t plus 1. Derivative of 2t is 2, and 1 is 0, so it's just 2. And then we keep the t minus 2. And divide by the denominator squared, so 2t plus 1 squared. Okay, so then notice in the numerator we have 2t minus 2t, so that cancels. So we have 1 minus negative 4 is 5, times 9 is 45. And then t minus 2 to the 8th in the numerator. In the denominator we have a 2t plus 1 to the 8th, and we have a 2t plus 1 squared, so that becomes 2t plus 1 to the 10th power. Okay, let's differentiate this mess. So before we had to use the quotient rule, looks like we have to use the product rule now. So this is 2x plus 1 to the 5th times the derivative of x cubed minus x plus 1 to the 4th plus x cubed minus x plus 1 to the 4th times the derivative of 2x plus 1 to the 5th. The product rule says you leave the first one, take the derivative of the second, plus the second times derivative of the first. Okay, so that becomes 2x plus 1 to the 5th times, by the chain rule now, 4 times x cubed minus x plus 1 to the 3rd. We just take the 4, drop it out in front, and then reduce it by 1. However, the chain rule says we have to multiply by the derivative of what was inside, so that's times the derivative of x cubed minus x plus 1. Okay, now we still have the entire second half of this expression, so that's plus x cubed minus x plus 1 to the 4th times now this derivative, so that's 5 times 2x plus 1 to the 4th times the derivative of what was inside, which is 2x plus 1. All right, let's see if we could simplify this at least a little bit. So we have 4 times 2x plus 1 to the 5th times x cubed minus x plus 1 cubed times 3x squared minus 1, because that's the derivative, plus 5 times x cubed minus x plus 1 to the 4th times 2x plus 1 to the 4th times 2. Okay, so notice that there is a 2x plus 1 to the 4th over here, and inside that there is also an x cubed minus x plus 1 cubed in both of these guys. So we can pull that out, and there's a 2 in both. So we pull out 2 times 2x plus 1 to the 4th times x cubed minus x plus 1 cubed, and we're left inside with 17x cubed plus 6x squared minus 9x plus 3. Let's differentiate y equals e to the sine x now. So the derivative is equal to the derivative of e to the sine x, which is equal to e to the sine x, because we're pretending it's e to the x, derivative of e to the x is e to the x, and then times the derivative of what's inside. which is just sine x. Okay, so that's e to the sine x times cosine x. The derivative of the exponential function b to the x is b to the x ln b. Notice before we tried taking the derivative of the exponential function and we ended up with itself times its own derivative at 0. But now we can replace that with ln b because we have the power of the chain rule, which is a lot better because how would we ever have known to even figure out what the derivative was at 0 in order to plug in? Okay, so if we have b to the x, that's the exact same thing as e to the ln b to the x, because e to the ln cancels, it just gives you b to the x. So that means that we can write that as e to the ln b times x. So that means if we're taking the chain rule, if we're taking the derivative of b to the x, we could use the chain rule, take the derivative of e to the ln b x. So that's just e to the ln b x, because you're pretending this entire thing is one variable. And then derivative of what was inside, so that's the derivative of this guy. So then we have e to the ln bx times, well, remember that this ln b is just a constant. It's just like the same thing as saying take the derivative of 2x, it would just be 2. Take the derivative of 10x, it would just be 10. So the derivative of ln bx is just ln b. Okay, so that's e to the ln b, so this cancels over here, and just leaves you with b to the x. So we have b to the x ln b. So you can see that this is actually pretty easy to apply, at least for this problem. We have derivative of 2 to the x, well that means b is equal to 2. So we're looking for the derivative of 2 to the x. Well, that's just 2 to the x times ln 2. Okay, let's find f prime of x if f of x is sine of cosine of tangent of x. So we want f prime of x, that's cosine, right? Derivative of sine is cosine of tangent of x. We're pretending that it's just cosine of whatever, so it's just sine of whatever, so the derivative is just cosine of whatever, and then times the derivative of what was inside. So that's cosine of tangent. Okay, so that means we have cosine of tangent times minus sine of tangent, because now we have to do the chain rule again, because derivative of cosine of tangent is a composite function of cosine and tangent. So derivative of cosine is minus sine, we pretend tangent is just one variable, and then we take the derivative of that. So this ends up becoming minus cosine tangent times sine tangent, and derivative of tangent is secant squared. Let's differentiate y equals e to the secant 3 theta. So in this case, we're looking for dy d theta because that's our independent variable. Oops, I said theta, but I wrote x. There we go. So that's e to the secant 3 theta, because e to the x has derivative of just e to the x, and then times derivative of what was inside. So that's secant 3 theta. So then we have e to the secant 3 theta times, well, derivative of secant is secant tangent. So we have secant 3 theta times tangent 3 theta. Only problem is that this wasn't derivative of secant, it was derivative of secant of 3 theta. So that means that this was a composite function of secant and 3x. So we have to multiply by the derivative of what was inside that derivative of 3 theta. Okay, so that's 3e to the secant 3 theta. We just moved the 3 out in front because derivative of 3 theta is just 3. And we keep our secant 3 theta, tangent 3 theta.